Okay, this is section 4.1, number 14, and here we're asked to find a solution, particular solution, or a solution to this differential equation if we're given a family of solutions here, and we're given boundary conditions. So what we have to do is use these two conditions to solve for C1 and C2. Now there might be cases where a solution does not exist. So let's check this this one here. So y of -1 is going to give me C1 -1 squared plus C2 -1 to the fourth plus 3, or C1 plus C2 plus 3, and that needs to be 0 from this condition. And then y of 1 gives me C1 1 squared plus C2 1 to the fourth plus 3. Again, that gives me C1 plus C2 plus 3, but in this case that needs to be equal to 4. Well, these two right here, you see already I can see there's a problem here, right? C1 plus C2 plus 3, it should be 0, but then it also should be 4, and it can't be both. If you don't completely see that yet, you can see from here that C1 is -3 minus C2. If I plug that in here, I get -3 minus C2 plus 3 equals 4. These cancel, this cancel, and I get 0 equals 4. And that's the problem. So there's no solution that satisfies these boundary conditions. Let's go on to another set of boundary conditions. So here I have y of 0 equals 3. So let's go ahead and find that. Y of 0 is C1 times 0, so 0 plus 0 plus 3 equals 3. And then I have y of 1, which would be C1 times 1 squared plus C2 times 1 to the fourth plus 3, and that needs to be 0. Now here I get 3 equals 3. This is true all the time. And then I have C1 plus C2 plus 3 equals 0, or C1 is equal to minus C2 minus 3. Since this is the only condition that needs to work, then this works for any numbers that satisfy that. So for example, if C2 is 1, then C1 would be -4. So based on whatever C2 is, I get a different value for C1. So there's an infinite number of solutions that pass through these boundary problems. Now if you check at 0, you can see that that makes the function in front of the y with the highest derivative be 0, and so that means that we are not guaranteed a unique solution. So this can happen, this type of thing can happen, infinite number of solutions. Finally, let's use these boundary conditions and we'll find a unique solution in this case. We'll see. So y of 1 is C1 1 squared plus C2 1 to the fourth plus 3, and that needs to be 3 from this condition. And then y of 2 is C1 2 squared plus C2 2 to the fourth plus 3, and that needs to be 15. So from this equation here I get C1 plus C2 plus 3 equals 3, and from this one I get 4C1 plus 16C2 equals 12. I have two equations and two unknowns. In fact, from this one I get that C1 equals -C2, so that I get -4C2 plus 16C2 equals 12, or 12C2 equals 12, so that C2 is 1, and that means that C1 is -1. Plug that into the original equation and we have our unique solution.